All right, so our next topic that we're talking about is generalizing this Hooke's law. So we've just learned into multiple dimensions. So in this case, what we now have is that the force is now equal to minus k times the displacement vector r. Now the nice thing is if we're working in Cartesian coordinates, then in this case, of course, Newton's second law breaks down into component form, which means that we can write fx is equal to minus k times x, fy then is equal to minus k times y, and then fz is equal to minus k times z in 3 dimensions. Of course, if I had more dimensions, I would just keep going. Now here, because of this, I'm assuming that each one of these spring constants is the same in all directions. This is what we call an isotropic oscillator. Now, of course, this doesn't have to be the case, and we'll talk about what happens if this is not the case, but for now, let's just assume we're working with the isotropic oscillator, and let's only look at, say, 2 dimensions for now. 3 dimensions won't be too much different from that. Now, again, Newton's second law, and that each one of these different directions says that, in the x direction, we have to have x double dot, that is equal to minus omega squared times x. And then we also have to have that y double dot then is equal to minus omega squared times y. Now, based off of Hooke's law, what we just talked about, each one of these guys now has its solution. So from here, x then would be equal to some coefficient ax. So this is just the amplitude that it has in the x direction. Times then cosine of omega times t minus delta x, which is the phase factor in the x direction. Simultaneously in the y direction, we'd have to have y that is equal to a y times then cosine of omega t minus delta y. Now from here, we can now do a shift in time. So for example, I can get rid of the phase factor here by shifting the time. But if I shift the time here, that's then going to introduce the phase factor over here. So we can introduce what's known as the relative phase. Let's talk about the relative phase. Where the relative phase, I'm going to call that delta, is then equal to delta y minus then delta x. So again, if I change the time, so meaning I'm going to rescale the time here to make this thing start off at, say, cosine. So in this case, it doesn't start off somewhere between, it only starts off at cosine. And then this one is going to shift its phase factor by that amount at which I change the cosine. So if I do that, and we introduce this then relative phase, what happens then is that, for example, we can rewrite this then as x is equal to ax cosine then of omega t minus, and then y is going to be a y times cosine of omega t minus that relative phase. So basically, the motion of this thing is then going to be dictated primarily by this relative phase. So one way we can see that is, so let's say that we have a relative phase. And let's talk about what actually happens in this case. So let's assume that neither ax or ay are equal to 0, because if ax or ay were equal to 0, that means it would only be harmonically oscillating in some particular direction. So for example, if ax was equal to 0, then it would only be harmonically oscillating in the y direction, which means that it's a one-dimensional harmonic oscillator, not actually a two-dimensional harmonic oscillator. Same thing as if ay was equal to 0, then it would only be harmonically oscillating in the x and nothing would be happening in the y direction. So let's assume that those two are not 0. And let's look at what happens for different relative phases. So first, let's look at if our relative phase is equal to 0. So meaning that these two things are in phase with each other. So what happens in this case? Well, in this case, if we solve this for cosine, we get that cosine then of omega t is equal to x divided by ax, which is also then equal to y divided by ay. So from here, this then tells me that what, ay times x must be equal to ax times y, which is actually just the equation of a line with a slope of either ay divided by ax or ax divided by ay. So in this case, if we rewrite it this way, this is now going to be x that is equal to ax divided by ay times y. So basically, what happens then is what? If I think about plotting this in a two-dimensional coordinate system, then as long as the relative phase is equal to 0, meaning that these two things are harmonically oscillating exactly the same, then in my xy coordinate system, this thing is actually just a straight line, which has a slope then of simply ax divided by ay. So, for example, let's say that what? Ax is equal to twice the size of ay. So that means that what? If this thing increases by 1, this one increases by 2. So this thing actually harmonically oscillates along the line, which in this case would be defined by this line. So basically, in here, this thing would just be oscillating along this particular line. If, again, these two things are in phase with each other. So if I'm looking at the x and the y. Now, what happens, though, if these things are not in phase with each other? So let's take the extreme case, where here, let's say that if delta is equal to pi over 2, then these things are completely out of phase. So in this case, this is going to stay cosine, but this one's going to shift the sign. So basically what happens in this case then is how this thing oscillates then is going to depend on, again, the ratio of these two amplitudes. But basically what happens in this case then is, again, I'm going to get x then is equal to ax cosine of omega t. And then we're going to get y is equal to ay times sine of omega t. Which means if I take cosine squared of omega t plus sine squared of omega t, that has to equal 1. But from here, cosine is the same thing as x over a, so this is going to be x squared over ax squared plus then y squared divided by ay squared must be equal to 1. But this is simply just the equation of an ellipse. So what's going to happen then is what? When these things are completely out of phase with each other, the motion is then going to be that of an ellipse, where this thing is going to have some amplitude along here, ax, some amplitude along here of ay, so that this is going to be, say, negative ay, this is then going to be ax, so this is then going to create, at least in the xy plane, some elliptical shape who's defined by its semi-major axis in the x direction and its semi-minor axis in the y direction. Now, anything then in between is going to, what? Have to go from somewhere from a straight line to somewhere this way, which basically means that this thing has to rotate into here. So basically, if I have any other relative phase difference between the two of them, what will happen in this case then is it's still going to be an ellipse, but it's going to be a rotated, tilted ellipse, and it's going to start to rotate into this direction. So for example, if we have, pardon me, if this was equal to pi over 4, they're not completely out of phase with each other, so they can't be in phase and they're not completely out of phase. So what will happen is we're still going to get some sort of ellipse, but now my ellipse is going to be centered again at 0, but it's going to do something more like this. So this will be its oscillation then in the xy plane. So again, this is only true when we have a isotropic, but of course we don't have to have an isotropic. We can have what's known as an anisotropic. So let's talk about an anisotropic oscillator. Well, an anisotropic oscillator is one where the spring constants, that k value there, is different in each different direction. So, is this color? So basically what will happen then is we get what? That fx is going to be minus kx, which is going to be the spring constant in that particular direction, times x. And then fy will be equal to minus ky times y, which means then that x double dot will be equal to minus the angular frequency squared in the x direction times x. And then we get a y double dot is going to be equal to minus the angular frequency in the y direction squared times that position. So, again, using the solutions, we can write down the solutions, but again, what's different is now the angular frequency is different into two different directions, which basically means that, what? Again, we can have a relative phase between the two. So following what we just did before, we get x then is equal to the amplitude in the x direction times cosine of the angular frequency in the x times time. But then in the y direction, we get y is equal to the amplitude in the y times cosine of the angular frequency in the y direction, minus, again, delta, where delta, again, is that relative phase. So here, the motion is going to be a little more complicated because now it's going to depend not only on the relative phase and the relationship between the two amplitudes, but now it's also going to depend on these angular frequencies as well. So depending on how these angular frequencies relate to each other will depend or determine the actual motion at which this thing does. Now it turns out that the motion is going to be dependent on the ratio of these two angular frequencies. Now it turns out that if the ratio between these two angular frequencies, if this is rational, what happens then is the motion in the xy direction will be periodic. So the motion in the xy plane is periodic. Now, but if this ratio is irrational, then the motion in the xy plane is chaotic. Now, what does that mean? So what that means is that it never repeats the same pattern twice within the xy plane. Now, that is not to say that it is not periodic in the x direction, and it is not periodic in the y direction, because it is simple harmonic oscillation. They are periodic in those different directions. But it's not periodic within the same, or at least within the xy plane itself. So what do I mean by that? So let's kind of plot out, draw a couple plots and see what this thing actually looks like. Now what ends up happening is the motion stays contained within a 2ax by 2ay rectangle. Now this is true regardless of if it's rational or irrational. So let's look at the rational case first. So in the rational case, let's say this is again my x direction, this is my y direction. Let's look at a particular example. So let's say that in both cases, we're going to go ahead and say that ax is equal to ay, just to limit our expectations here. Or at least on normal variables. And let's look at when the angular frequency in the y direction is twice the size of that in the x direction. So basically, what happens in this case then is we get a pattern that kind of looks like this. So we get something that's like this. So this is a periodic motion within the xy plane. So this thing follows this path all the time. Where again, this is going to be what? Negative ax. This is going to be ax. This is going to be, say, ay. And this is going to be negative ay. Said they were the same. It doesn't look that way, but that's okay. We get the idea. So again, this thing is simply going to oscillate like this. So this, whenever this ratio, again, is rational. So again, here, omega x divided by omega y is then equal to what? 1/2, right? Good. So let's look at the other case where this guy is irrational. So if this is irrational, so what happened is if this is irrational, so say for example, we have omega y is equal to the square root of 2 of omega x. So if I look at the x, y plane, what will happen is this will start doing some sort of motion. It's kind of a hard motion to draw. But let's say this thing, I don't know, starts off something like here. So let's say this is ay, negative ay, ax, ax. So this thing's going to start in some motion. Let's say, I don't know, it starts like here. It's going to come around. Let's say it goes down like this, swings back, going to come over like this. It'll come back here. It might come infinitesimally close to possibly the same thing, but then misses and then keeps going. So eventually what will happen is this thing will end up oscillating, but it's never going to repeat the same pattern twice. It's just going to keep going until eventually what's going to happen is this entire rectangle that is described by this 2x by 2y will eventually become completely filled in. So all the motion will be contained within inside of this rectangle, but it'll never repeat the same pattern twice. So it'll get infinitesimally close, and it'll become approximately the same, and it'll get very, very close to what's actually happening, but it'll never actually do exactly the same thing, which means it's going to be closer to a chaotic type motion. But again, this thing is, if I'm looking only in the y direction, this thing is rhythmically oscillating in the x direction. It is oscillating exactly with the same pattern in the x direction, but the incompatibility between the angular frequencies will then cause this thing to never repeat the same path twice. So this becomes more of a chaotic type situation, where here this thing will always go with exactly the same shape. And again, as you choose different ratios, this pattern that which it maps out will be different depending on the value of the ratio between these two guys. So this is multiple dimensions for harmonic oscillation.